Hello students, welcome to Inside Physics. Today we are going to discuss about the polarizability or polarization of a dielectric material and how it actually varies with the applied frequency. When you are applying an alternating voltage to a dielectric material, the polarization is nothing but net dipole moment per unit volume of a dielectric material. How it varies with applied frequency. Here the frequency is nothing but the frequency of oscillation of an alternating current. You know, the alternating current is always displaced by a sinusoidal curve, because the sinusoidal curve actually represents the positive side and negative side, and this is maximum voltage and this is also the maximum voltage that you can apply. This is on the other side. So in this way the alternating current is applied, and here in this session we study the polarizability of dielectric material when we apply different frequencies. We all know that total polarization. Polarizations are four types: electronic, ionic, and orientation, space charge polarization. We already derived those mathematical relations in the previous videos. The total polarizability is given by 4 pi epsilon naught r cube. This is regarding electronic polarization, and for ionic polarization you can take it as the relation as, and the finally the orientation polarization is given by with this formula. So total polarizability of a dielectric material, sometimes some materials will possess all the four. The space charge polarization we consider as very negligible, so we take it as 0. This is electronic for electronic polarization, this is for ionic polarization, and this is for orientation polarization. Three terms, and here the charge of electron and the vibrational frequency of the electron, and here see the third term mu square is the mu is dipole moment, total dipole moment of the dielectric material. Kb is Boltzmann constant, T is absolute temperature of the given gas. So when you consider this as a total polarizability, and we have another mathematical relation for polarizability at a particular instant of time, that is given by instantaneous polarization is given by 1 minus exponential minus t by tr. Okay, this is the polarization at any particular instant of time. This is the time, and tr is the relaxation time. Relaxation time is the reciprocal of relaxation frequency. Relaxation frequency is nothing but, see, this time, relaxation time is given by the time, average time taken for a dipole to completely orient into the electric field direction when we apply an external field. So this is the average time of a dipole. We have so many millions of dipoles in a dielectric material in the form of atoms, molecules, or ions. So each atom or molecule behaves like a dipole, and it takes into the orientation, it itself diverts into the in the direction of the electric field, that is called what we call polarization. So in that process each dipole has some time lag in actually converting it into the direction of the electric field. So the average time of all the dipoles is taken as relaxation time. So this is the instantaneous polarization, and P naught is the maximum polarization up to which a dielectric can be polarized. So here next we see for different frequencies how this dielectric material behaves and how its polarization changes. We have seen here there is a graph which is given in the form of angular frequency on x-axis, and this you can take it as 0, and this is polarizability. You can see at different frequencies. At microwave frequency, the see this is the frequency, the polarizability is almost going down, and actually at near the infrared region it has some small peak. It actually rising and again coming down nearby the infrared frequency region. And at ultraviolet region, see this is a graph which actually picturizes the polarizability variation with the frequency. We have taken some different frequency zones: microwave, infrared and ultraviolet. You can see the dips and the columns which are moving up. So here if see in the ultraviolet region there is a increase in the polarizability up to some extent, and again the sudden drop. So at the frequency zones of some frequency regions there is a sudden uplift and again sudden down of the polarizability. So this we can have an explanation by seeing the different frequency applications and what happens exactly at the frequencies. You see, at audio frequency means the audible frequency, 20 hertz to 20,000 hertz, 20k hertz. So at this frequency, as the frequency is somewhat lower, all the dipoles will comfortably, step by step, they will orient into the direction of the field. So in that process, there is no power loss. Okay, the field alternations actually result in the slow shifting of their orientation of the dipoles into the direction of the field. So next, at radio frequency means it is a long range wavelength, which are the waves will have a long wavelength. Obviously the frequency is smaller. At smaller frequencies, see the dipoles actually doesn't have time. They actually neglect to orient in the direction of the field because of the thermal agitation and the friction between the molecules. For a small frequencies they cannot actually come into the direction of the field. So consequently the dipoles lag behind the forces that cause the motion. Because of this, a phase difference develops between the polarization and the electric field, resulting in a fall of the polarizability. So here energy supplied to maintain the rotation of the dipoles is actually accounting for power loss. We supply the electrical energy in the form of alternating current at this frequency, but the dipoles are very reluctant. So there are some frequencies which they can happily convert into themselves into the direction of the field, and there are some frequencies it's very difficult for them. They have so many obstructions like thermal agitation and friction between the dipoles. They all come into picture, and obviously the polarizability will come down just like here. This is sudden sharp rise and there is a sudden sharp downfall in this case. So the up and down of the frequency will also causing the polarizability variations. Near relaxation frequency, what is the relaxation frequency means? It is the reciprocal of relaxation time. I already discussed what is relaxation time. So at this frequency, the dipoles will come into the direction of the field, orient themselves into the direction of the field very rapidly. So there is no power loss here. When actually every dipole is coming into the direction of the applied frequency, and the relaxation frequency is nothing but the frequency is matching with the frequency of orientation of the dipoles. Then that this frequency, the polarizability is maximum. So, and the if there is maximum polarizability, the power loss, all the dipoles are getting themselves oriented, and there is no point of reluctance in this kind of motion. So, obviously, the power loss will come into minimum. So, here at near relaxation frequencies, the power loss is minimum. So, what happens above the relaxation frequencies? So, above relaxation frequency, the electric field reverses so rapidly that the dipoles cannot follow the field reversal due to inertia. Okay, and the inertia is because of their position and mass. So, this above relaxation frequencies, the polarizability will decrease, and there will be a definite power loss because they are actually unable to orient themselves into the direction of the field, and just above the relaxation frequency, they almost come into the direction, but they cannot completely come into the direction. At much higher frequencies, what happens at much higher frequencies? See, as here there is a bell shaped profile with a maximum at the molecular dipole relaxation frequency and reaching zero on either side. See, when the loss of electrical energy is greatest means, see, at much higher frequencies, the orientation will not be 100%. So, at this, the dipole orientation is not reaching the maximum, the fullest. So, at this kind of polarizabilities, the power loss will be maximum. So, it almost the polarizability, see here it has come to 0. Polarizability has come to 0 here because at these higher frequencies, see, the polarizability is coming to 0 means there is a higher power loss. Next, at lower frequencies. Lower frequency is nothing but like audio frequency, what we have seen. Obviously, they are very comfortable with the frequencies. Lower means here we can say lower than the relaxation frequency. If there is this is a, see, if we can draw a curve at relaxation frequency and other both sides of this frequency, the polarizability is not 100%, exactly nearly to the frequency here, the power loss will be maximum, just nearer to this relaxation frequency, and we can almost say both points are taken just above the relaxation frequency and just above the relaxation frequency and just below the relaxation frequency. At lower frequencies, the power loss will be maximum because that is not a comfortable frequency for the dipoles. At infrared region, here I have given the region here. What happens at the infrared region? The infrared radiation is nothing but heat radiation. The heat energy will obviously be in that kind of region, and the free heat is an electromagnetic wave, so it has a frequency. But here we are not talking about the heat energy, but its frequency zone. At infrared, region, frequency zone, what happens? The ionic dipoles follow electric field variations. See, when one constituent of the dipole is displaced relative to the other, it again experiences a restoring force proportional to the displacement and executes simple harmonic motion. What happens? You see, when you take an example of ionic polarization in infrared region, the dipoles execute simple harmonic motion because of the variation of frequency. See, if it is an atom having some dipole axis like this, it will be oscillating in the frequency region, and the alternating current is also an oscillating frequency. So it will make some simple harmonic motion which causes the power loss. If this is in analogous to the applied frequency, the power loss will be minimum. If there is a phase difference or time lag between the oscillation of the dipole and the applied frequency, the power loss will be more. Here, next one, at natural frequencies, every dipole or atom or molecule is having a natural frequency. See, every object, every particle in the universe and the constituent subatomic particles is having a natural frequency. So the natural frequencies are also having some effect on the applied frequency. Generally, the oscillating natural frequencies are in between the region 10 to the power of 13 to 10 to the power of 14, 13 to 10 to the power of 14 hertz. So in this region, the natural frequency zone, see, the power loss is also minimum because they have a natural frequency, and this power loss is called resonance loss. Okay. Next, above the natural frequency. What happens above the natural frequency? Just we discussed at much higher frequencies of the relaxation frequency. Here above natural frequency, so the frequency is actually not matching with the natural frequency of the atom. What happens generally? It actually defies to come into the frequency of the applied frequency, and there will be a friction, there will be a phase difference. Whenever there is a phase difference and the orientation, the polarizability will come down. So that is the cause above natural frequencies. See, here the power loss is there, and the power is absorbed when the field exceeds their natural frequencies. The losses encountered in this process are known as resonance losses. Obviously, here also the loss, here also the power loss is called resonance power loss, because whenever the natural frequency is matching with the alternating frequency, there will be a resonance and the polarization will suddenly increase because of the resonance polarization. The last one, at optical frequencies. Optical means the optical zone, the visible light. It has actually the wavelength is roughly between 400 nanometers to 800 nanometers. So this is the wavelength region of visible spectrum. So here the frequency of the visible region, again this is called the optical frequency. In this optical frequency, the electron clouds actually vibrate in the total dipolarized the dielectric material at optical frequencies. So what is the frequency optical frequency, and when it is actually matching with the natural frequencies, which are almost 10 to the power of 17 to 10 to the power of 18 hertz, the optical frequency zones will make the electron clouds vibrate, and they actually do the simple harmonic motion at optical frequencies. See, here also there will be some losses because they re-emit this energy in random fashion. Whenever the light is fallen onto the dielectric material, the atoms or molecules do the simple harmonic motion, and they also vibrate, and they re-emit the light energy. So what happens when they re-emit the light energy? That is called, we call them as reflection. So what is the concern here with the polarizability means, in this process subsequently these electrons fail to follow the excursions of the field and cannot absorb the power anymore. So here the power absorption is very less because of the frequency. This is how we understand the polarization, frequency dependency of the polarizability or polarization. In the next session we will come with some good topic. Okay, thank you.